Yes. Has it started recording? Yes, now it is. Okay. So, good morning once again to all of you. So, today is our lecture 4, right? So, this is the fourth lecture. And in this class, we are continuing our discussion on this inverter. And we have started our discussion with a basic resistive load inverter, right? So to give you a type of recap, what we have discussed in the last class very quickly, or otherwise we will spend a lot of time in only doing the recap part. Yeah. So we have started from here, right? We have started from the regenerative property of this inverter. Then we have tried to understand what is the noise margin analysis in case of resistive load. And we have done one example. It's not type of numerical one, but one type of analytical one. But obviously, if the values are given, you can always, uh, find the values, right? And you can always, from here, you can find this noise margin high, noise margin low, which is to what, these are the very important, right? Very important parameter in case of any digital IC design. Then also we have done one very basic, one small example, and we are trying to understand what would be the requirement in case of this W by L ratio and this RL, right? Because we have seen that if you want to decrease this V of OL, right, or if you want to keep on VOL dash to a fixed value, then for that value, how you can achieve it? You can achieve it in two ways. One is this by changing this W by L ratio, or by changing this RL, or the load resistance, right? So, and while discussing that, we have seen if you are increasing this W by L ratio, then obviously you can go with lower, or work with lower RL. But in that time, in that case, particularly, your power dissipation is significantly increasing, right? So, if the power dissipation is one of the major consideration, then what you have to do, you have to probably take a higher value of RL and lower value of W by L ratio, right? So we have understood this part, right? Okay. Then we have also discussed like what about the slope? Okay, how this slope is depend, or this slope is also dependent on this Kn into R, right? We have seen that if this Kn into R, this value is increasing higher and higher, then obviously the slope is also becoming higher and higher, right? That also we have discussed. The same context we have also discussed that for this type of inverter, if this RL is much higher, right, then the effective resistance for during the charging of this capacitor is much higher compared to the discharging, and that basically gives rise to the asymmetrical switching characteristics, which is one of the another issue for this type of resistor, for this type of design, right? Right, then while discussing this chip area, we have also come across this to the MOSFET area. MOSFET area is basically defined by this W into L and the area of this resistance. And while discussing the resistance, because right now MOSFET is not the major focus of at this point, because MOSFET fabrication we will discuss separately. Right. Now let us focus on this RL part only. Now, while discussing this RL, we have seen that RL can be managed by or fabricated by this diffused resistor or polysilicon resistor. We have briefly discussed how they are fabricated. If you have missed that class, please revisit those things. These things are important. Here we have introduced one term which is called the sheet resistance. And we have also mentioned what is the typical value of this sheet resistance in case of if you are making this resistor by diffused resistor or polysilicon resistor, right? So this is all everything that we have done in the last class. Now to discuss with what is this sheet resistor, we have discussed from here, we have started our discussion from this, right? So sheet resistance is basically the resistance of a very thin film, right? You can think that way as well. So while discussing this, we have seen that this resistance can be interpreted as this rho by L into L by W, and this rho by T, that is the resistivity per unit thickness, is nothing but the sheet resistance. But if you consider it from a unit point of view, then basically you can also see the sheet resistance unit has to be only same as that of this resistor, right? But to differentiate it with a normal resistor, what we have generally write, it's basically ohm per square. So what does this square mean? The square means that if you have made, suppose you take any length and you make a square, we are considering the film thickness remains the same. Then this, this whatever this portion, if this resistance is offered, if you say the sheet resistance offered by this is RS, right? And then if you change the length of this sheet by 2 times and also the width of this change by 2 times, then also for the bigger sheet, that is for this one also, sheet resistance is going to be the same, because you can see the sheet resistance is right, it's actually independent of this length and width, this ratio, right? So if you fix the length, right, for example, you can see here we have fixed 1 micrometer this width. Then if you increase it, if the length is the 1 micrometer, then it's RS. If you take one more RS, one more 1 micrometer, then it is, this portion is RS, this portion is another RS. Then if you calculate the sheet resistance between these two terminal, right, then its effective resistance would become 2 RS. Effective sheet resistance would become 2 RS, right? So this is the concept of this sheet resistance, right? Now we will continue with this sheet resistance only, right, and see that some type of physical interpretation, or in this context, right, resistive inverter context, we will see that how this sheet resistance comes into, we can introduce this concept sheet resistance, and from here we will try to simply try to see one more difficulty which is associated with this type of resistive inverter design. One we have already discussed, right? One is this asymmetrical switching characteristics. Right. So let us then start quickly today's class. So today we are discussing this constant, we are continuing, right? It is an inverter with resistive load. So this is the circuit design, right? The issues, as we have discussed, asymmetrical switching time, that is T charging and T discharging. They are different. T charging is this way, T discharging is this way. This resistance is much higher, that we have already discussed. So basically T charging and T discharging, they are different, right? And the R value has to be quite large, right? From the power dissipation point of view. That also we have discussed in the last class and briefly also today. Now then, what is the implication of this large value of resistance R, right? Okay, and do you recall what was the resistance actually? Anyone recall? What was the value of resistance for lower power dissipation, for the lowest power dissipation in our previous example?
Sir, 205 kilo ohms.
205, okay, say 205 kilo ohm. So R is 205 kilo ohm, right? Now let's see that we are fabricating this 200, well, we want to fabricate this 205 kilo ohm resistor, okay, in semiconductor technology, in some particular any node, say, right? And let's see that how the sheet resistance can be introduced, the concept can be introduced here, and see from here sheet resistance, what can we infer, another limitation, okay, for this type of design, right? So in this context, let us say we have used the diffuse resistor, diffused resistor technique, diffuse resistor technology. That is this one, right? Quickly, okay, that is this one. There are two types. There are two types of techniques. One is the diffuse resistor, which we have discussed, which is fabricated like this by diffusing, right? And when you diffuse it from the top view, if you see, it has a particular width, right? This has a particular width, right? And we have mentioned this width to be in the range of 1, say, micrometer, right? It's not the polysilicon based one, but we are for this technology we are using this diffuse resistor type. Okay, and say the sheet resistance was here 20 to 100 ohm per square. Okay, so we have used diffuse resistor technology, and here the sheet resistance RS is how much? Say the lowest one, okay, 20 ohm per square, right? And say for this technology, the width, okay, the width is equal to 1 micrometer. Width, you understand, this means, that means this is 1 micrometer, this width, right? That means you will give one connection here, means the current will flow from here to here. This is the flow of current, right? And this is 1 micrometer, right? Now if you know, if you make also 1 micrometer in this side, then from here to here this resistance is 1 RS, right? Now if you add one more, then it become 2 RS, then if you add become one more, then it become 3 RS, like that, right? Okay, so then we know that the total resistance R is equal to 205 kilo ohm that we have to design, right? And RS is this one. Now we also know that R, we can write it like R equal to RS, heat resistance, into length by width, right? Now what is this width? Width is 1 micrometer, right? So then what is length? Length is equal to R into width by this RS. Okay, so what is here? 205 kilo ohm. What is this width? Width is 1 micrometer. And what is this RS? RS is how much? 20, right? 20 ohm per square. Okay, so could you please calculate this and tell me the value of this length? Please tell me the value in millimeter.
10.25
10.25. What unit?
millimeter.
Okay, I have not calculated it. So please do cross check this one. Okay, so 10.25 millimeter. So that means you understand what is the implication physically. That means if you are making a register, means diffuse it. So that means if this is, say, obviously this is scale, this drawing is not in scale. If this is 1 micrometer, then you need a length of 10.25 mm, right? So that the resistance between these two will become 205 kilo ohm, right? So this length, see this length is 10.25 millimeter, but while in semiconductor, this is too large, right? So for semiconductor or for VLSI, the most important constraint is the area, surface area. We cannot compromise with the area, right? So as this area requirement is very constrained, so from that point of view, you understand, right, that we cannot make a very high resistance in this semiconductor technology node, right? Because transistor dimensions are nowadays in nanometer, right? Transistor, right? Transistors are in nanometer, but here see it is in millimeter, but R is in millimeter. So obviously this technology is not that way useful. So we have to find some technique by which we should be able to replace this R. Okay, we should be able to replace this R. So we will see in the next example only. There is an way that is this R can be replaced by a MOSFET as well. And you know, as MOSFET takes very less area, so that would be quite means then our next design would be quite better in terms of space requirement, right? If we can replace this R with a MOSFET. Right? So this is the verdict that we have reached from here, that this is not a good design in terms of VLSI technique, right? Okay. Now, so another issue you understand. So R value too large. So this, and too large means what is the implication? Implication is area requirement is too large, right? Then not suitable for VLSI, right? So remember, this is the next one. Okay, remember, okay, let me ask you, do you think, is there any other issue with this design? Quickly. Let's see who can answer this. Abhishek, Auditro, Ayushi. This will also check who is attending or who has only, or you have only logged in and then left. Gautam, Harsh, I am not getting any response.
So can you please repeat the question?
Yeah. Do you think is there any other difficulty or any other issue with this design?
So are you talking about the robustness of bias point?
Robustness of bias point, maybe more fundamental. No, we're not getting any other issue. Okay, let's see this. Power dissipation when V in is equal to VDD. See, when you have set V in equal to VDD, then this transistor is on, right? So as long as V in equal to VDD, this transistor is on, you have a direct path from VDD to ground, right? Current will continuously flow through this resistor and that will dissipate the power. So that means whenever you make this, if you give logic 1, you give logic 1 to this inverter, or as long as this inverter is in its logic 1 state, it will continue to dissipate the power, right? So that is called the static power dissipation. So power dissipation, better to say it as static power dissipation. Is that part clear to you, Nandaram?
Yes, sir.
Okay, Tarun, is this clear to you?
Yes, sir.
Okay, then can we move to the next section?
Yes, sir.
Sir, for the minimum power dissipation, we have made R to be very large. So I
Right.
mean, so how this static power dissipation is a issue here?
Oh, how this static power dissipation is an issue. Okay, say
I mean,
this R is,
power
say this
dissipation-
R is large, right? Fine, R is large, right? But whenever you have given V in equal to VDD, right? Then you see there is a direct path from VDD to ground, isn't it? Maybe this resistance is very high, so that means the current is low, right? But it's still there is a path from VDD to ground. Na? So that means as long as you keep this inverter is at give logic 1 at the input of this inverter, you have a direct path. So that means you have an static power dissipation. Shubhayan, is this clear?
okay, sir, but still we can't minimize the power dissipation less than this, right?
No, we can. We can. Suppose instead of this, if we can have some component here, some type of load, which suppose when this V in equal to VDD, if this switch off, or if this does not conduct this load, then there will be no direct path from here to here,
Yes.
right? Then it is possible, na?
Okay.
You understand? And eventually we are going towards
Okay.
that. In CMOS, it is possible, right? And that's why, we are going towards that CMOS only, but step by step. Okay, how that things has evolved. So you understood this part, right? So one is this static power dissipation. Third one is the large area. I mean, second one is the large area. And the first one that we have discussed here, asymmetrical switching time, right? Okay. So in the next part, we will take only one of the disadvantage. That is one of the issue, try to solve it. That is the R value is quite large. So first or foremost, we have understood we cannot use any resistance. We have to replace it with some MOSFET only, right? So we have to reduce the area. So the next step, we are considering only the area part. Okay, and let's see how we will means how we will do in terms of static power dissipation there as well. Right. So the next design would be this NMOS inverter with enhancement load. So what do you mean by enhancement load? Enhancement load means it is basically a MOSFET. Say this is a MOSFET, again N-channel MOSFET. By the way, here I should say it beforehand only. We will be using this symbol for NMOS and this symbol bubble, and with this, so there in the bubble, right? This is for PMOS. Okay, so please do remember that. Huh? This symbol NMOS is this, PMOS is this. So for this NMOS, suppose if we connect these two terminal, okay, this is gate to drain terminal. Okay, then can you comment if you now, okay, say now you have grounded it, okay, and you have applied to a voltage source which is changing and is changing from 0 to VDD. Okay, You are changing this voltage source from 0 to VDD. So, and so obviously when you are changing this, you have a current, which is ID, right? And suppose I want to plot this ID versus VDS. So basically ID, VDD, VDS is nothing but the supply voltage for this case. So could you please guide me how the IV, this ID, VDS characteristics would look like for this MOSFET?
Sir, I have a doubt.
Yeah.
Sir, in the previous slide, you
Hmm.
told that if RL is increased, then the power dissipation increases if Vin is 1.
E power,
Vin is VDD, basically.
right? V in is equal to VDD, right? Hmm.
Yes, sir. But in previous class, what we actually did was that the average power dissipation would be minimized if RL is large.
Yeah. So
Oh,
are they not okay? Let me go to that and then okay. See here we have discussed the average power, right? Why? Because we have seen, suppose what is the on state means when you have given logic 0 and logic 1. Basically, you can see that when the input is at logic 0, there is no power dissipation, right? When the input is at logic 1, then there is a power dissipation. So we have taken an average. So we are interested to find the average one. If suppose in when the input is also 0, there is also some power dissipation. Then this number would be a bit different, right? But
yes, sir.
you understand my point,
Yes, sir. Got it.
right? Okay, so can I continue from where I left?
Yes, sir.
Okay. So then could you please tell me if I want to plot this ID versus VDS characteristics for this type of circuit, so how does that look like? We are starting from 0. Hey, please tell me quickly. We have to do it, na?
Same as a diode.
It will be like a diode. Okay. So tell me, important, we are started from 0 till say VTH, threshold voltage of this MOSFET. So what would be the current?
0.
Hmm. After that,
Will increase
Quadratic.
increase how? Linearly?
exponentially.
Exponentially. How do you know that it will increase exponentially?
Power of 2.
Power of 2. Okay. Why? Why? Because in MOSFET, there are two equations, right? So how do you know that only that square one will be will appear here, not the other equation?
Like
Actually,
This
if
is a
the
sir.
voltage is
shortage
greater than
voltage.
VTH, it is always in saturation.
Right.
So
So you
VDS is
see
equal
for
to
this design,
VGS.
right? If for this design you see this, that this transistor is always in saturation, right? This is always in saturation, right? So if this transistor is always in saturation, then that means it is basically VGS minus means ID would be proportional to say VGS minus VDH square, right? What is VGS here? See this V, okay.
VDS.
VGS is here exactly because G is equal to D, right? So basically ID is proportional to VDS minus VTH square, right? So that means from here to here it will be 0. Then after that it will follow this square law, right? So it will probably look something like this, right? Okay. So is this clear that this characteristics will be like this, right? Okay. So suppose instead you now think you want to plot the IV characteristics of, suppose this is also then that VDD which is varying 0 to VDD and this is ground, right? Then if it is resistance, then it would have come probably something like this, right? It will be linear, right? But instead if you use this transistor, then what you get? You get another IV characteristic, some different IV characteristics which is not linear, right? But it is behaving type of a load, right? Like this. So this type of arrangement or this type of connection is called the enhancement load, right? But here the advantage you can obviously see from this that we are now able to replace this resistance or resistor which takes a very large area by a very small transistor, right? So then what we are going to do? We are going to connect one this is G, this is S, this is D, right? So this is basically the load, right? Earlier we have an resistor here. Now we have replaced with this transistor. Okay. So now you see, this is the normal transistor, right? That this also we have used earlier. So obviously the ID VDS characteristics would look something like this, right? Now for this, the current voltage characteristics would look something like this. Now you have to tell from here, if I want to get the VTC, that is V out versus V input, right? For that we have to plot, right, this and superimpose means on top of these characteristics and these characteristics, right? Then we will get the intersection, right? And from that intersection we can find this V output versus V in characteristics, right? So please think for a minute and then tell me how we can superimpose these characteristics on top of these characteristics. Our goal is we have to find the VTC.
So VDS of ML is equal to VDD minus VDS of MD. So we can transform the axis.
Okay. So please suggest how. You are right.
Giving a positive shift towards positive x-axis with VDD.
So we have to like
Let's see.
invert this and then shift it and then superimpose.
Very good. So we are given this term here, ML, to indicate this transistor, that is a load, and MD to this transistor to indicate that this is a driver. So driver and load. We will indicate here by this term KD, that is, the basic transistor parameter, right? KD. And here we will put it at KL, right? Okay. Then can I not write that VDS, right? VDS load, right? VDS load is equal to this VDD minus V out. Can I write this? Tarun? Aniket?
Yes, sir.
Okay. Then
Yes.
what is V out? V out is VDS load. This is driver, right? So this is VDS driver. Can I write this? VDSL is equal to VDD minus VDS driver. Please say yes or no.
Yes, sir.
Okay. Then can we not? Okay. So this is the characteristics, right? This is basically VDSL. So we can see if we have to translate this axis on top of this axis, then what we have to do? We have to first make an inverse, right? We have to and subtract it from VDD. So this is VDD. So subtract it from VDD. So we have to. So this basically got flipped, right? You have to flip it and then plot it from this side to this side. So again, till VTH, there will be no current. After that, there will be right. This is again not a very good drawing, right? So what you have to do, you have to first flip it and then started plotting from here. So it is VDD. So I hope you are getting right. You place a mirror here, you place a mirror here. Whatever you will get, you have to put starting from this point VDD. So that will give you the. So basically here, this is a load line, right? Here, this is basically the load line. In case of earlier case, you have a load line which is a resistor, which is a straight line, right? But this is a non-linear one. So you also have the non-linear one. So clearly from here, you can see then till this point from 0 to this part, you will not have any current. Then you have a intersection is this. So obviously now I think you can now you know how to plot how the VTC will look like. So VTC Okay, I should not assume. Let me ask you. Yeah, please guide me to draw this VTC. Let's see who have understand. Yeah, what will happen from 0 to VTH? Alisha?
0. It will be
Uh,
VDD.
no, no.
It will
From
be
0 to
VDD.
VTH,
VDD.
it would be
VDD.
VDD. It would be VDD. Are you sure? Will it be VDD? Hey, tell me quickly. Will it be VDD?
No, sir.
So
Because
VDD minus VTH.
VDD minus VTH. Okay. Why you say it is VDD? It is VDD minus VTH. VTH, which one? L or D?
It's the upper one.
L.
L. Load one. Right. Because you see, when this V in equal to 0, so that means you can say like you have a characteristics which is like this, right? 0. And where it is touching with this curve, it is here, right? It is here. And what is this point? So this is VDD, right? You have to go one threshold voltage below, right? So this point is VDD minus VTHL. So this is VTH L, right? This part. Okay. So after that, what will happen? You see, it will be from here, it will go to here, then this point, then this point, then this point. So it will gradually fall. How it will fall, linearly or in a some parabolic way, that you have to tell me later on, and or we will see. So it will fall. Okay. So after that, it will go something like this and become like this. Okay. Now tell me, can it go to 0? Can minimum output voltage or VOL dash become equal to 0 for this case? Hey, you should be able to answer this. Bemula, Jash Agrawal, Ranveer Singh. Ranveer?
Yes, sir.
Yeah. So can VOL dash for this case become equal to 0? You are not concentrating, I guess. Rahul?
No, sir.
No. Okay. So no means you don't know, or it will not become equal to 0. Which one?
It will not become 0 because there will be some current and VDS, some
Yeah,
VDS will be
and
required.
also from this you can clearly see, right? This is the cross section. So minimum it can reach up to this part, right? It cannot be lower than this, right? If this is V in equal to this VDD, right? Then it cannot go below this point, right? V out. This is basically the V out, right? So minimum value is this. So it cannot go, right? So from this, without doing any mathematical analysis, what we can clearly see that for this type of design, yeah, we are able to replace this resistance with a MOSFET. So uh, we are able to save a lot of space, right? So that from that point of view, it is a good design. But for previous case, the VOH dash was equal to VDD previous case. But now for this type of design, neither the top output voltage means highest output voltage, or nor the lowest output voltage is equal to the rail voltage. Rail voltage means 0 and VDD, right? So this is minimum output voltage is higher than 0, and maximum output voltage is lower than VDD. So obviously, from this brief discussion, you can understand again, even though this solves that issue of large area, but it is again not a very good design. right? Okay. I hope this part is clear to you. If this part is clear, then probably we can move little bit, do some little bit analytical on this analytical analysis and then move forward. Okay, so again, this is the circuit design and this is the you know, characteristics of this MOSFET. So this is for MD and this is the characteristics of this ML, load resistance, or load means the load basically, not resistance, is load. So it would be like this, right? And so the same thing that we have discussed. And here, this is the threshold voltage. So this is basically VDD minus VTH, right? Okay. Now tell me, so you have understood when this V input is equal to V input is up to this, right? Then the transistor means this transistor is off. Then this V output would be equal to VDD minus VTHL, right? So on the other way, maybe we can write it quickly. So when this VDD is less than VTH D, the ML is so MD is in cutoff, right? So when this is in MD is cutoff, that means ID is equal to 0. When this ID is equal to 0, same ID is flowing through this load as well, right? So we can write 0 is equal to KL by 2 into VDSL minus VTNL square, right? Okay. Again, VDSL can be written as VDD minus V out, right? So that way, from this equation, we can write VDD minus V out minus VNL equal to 0. So V out would be equal to VDD minus VTNL. So also here you can see from that we can also show it like this, that V output would be equal to VDD minus VTNL for this part, right? Okay. Now next condition, when this V in is greater than VTHD, right? Aha. Have I done everything correct? Can you please check? Have I written everything correctly? Tarun?
So I think it should be VTH low.
True. So it is VTH load, right? So when this is greater than V in is greater than VTH load, right? Then what will happen? Then you can clearly see this transistor that is MD.
So can you explain why that would be VTH load?
Sir, it should be
It
VT
should
driver.
be
It,
VTHD.
it should be VTH D or VTH low.
If
So it
MD
should
is
be
in
drive. Yeah.
cutoff, then
So then VTH driver, right?
Yeah. Yeah. I think, yeah, you are right. See here, because we are now we have applied V in here, right? So V in is this one. So until and unless this V in is greater than the threshold voltage of MD or the low this driver transistor, that this transistor would not be on exactly. So it would be D only. So when this V in is less than VTHD, right? Then this obviously this MD is cut off. So when this MD is cut off, then ID is off. So ID is equal to 0. But this transistor, that is this load transistor, from this configuration itself, it should be always in saturation. So we can write the saturation equation for this transistor, and get the equation for this. Yeah, so it should be D only. So again, I was right earlier, right? So now if this V in is greater than VTHD, right, then what is this in which region this MD will operate? So you can clearly see this is the MD, right? So MD is operating in the saturation region, right? MD in saturation. Okay. What about ML? What about ML?
Is always in saturation.
It is always in saturation, right? It is always in saturation. So then can you construct a equation between V output and V input, okay, for this range when this V in is greater than, that means from here till here? Can you construct an equation? I think definitely you can, right? So what would be this equation? So just simply KD by 2 into this VGSD minus VTHD, that is square KL by 2 VGSL minus VTNL, that is square, right? And if we write if we simplify it, and finally we will get that VDD will be equal to VTNL minus root over of this KD by KL into V in minus VTND. So what this particular equation, please look it carefully, what this particular equation is suggesting that this V out is related with V in a linear fashion, right? So that means in this region, that means in this particular region, V output versus V input would be linear. So that means if we can go to here, that is this region would be a linear region between V output and V input, right? It is very easy to understand from here. Just make the equation. Okay, you know the equation, right? Just write it and finally you get an equation with V output and V input. That's way you can go back to this VTC characteristics and find what would be the nature of this curvature or the nature of this particular line, right? Okay. Now you see, if you consider now a situation here, right, from this point onwards, okay, from this point onwards, that is from C point onwards, right, this transistor, that is the MD will be in the triode region. However, ML will always be in the saturation region, right? So if I can write, that is beyond point C, right? If we say that beyond point C, this MD is in triode region, but ML is in saturation region, right? So that way you can also construct an equation, all right? And you can also find a relation between V output and means relation between V output and V input, right? So that means you can also find a relation between V output and V input for this region. Okay, so obviously this will not be a linear relation. Okay, so please try to find out, okay, what is this relation coming between V output and V out input for this region. Now here comes the question. Okay, what would be the point, okay, beyond which it will deviate from this linear to this non-linear region, right? So that means, can you please tell me what would be this point C, or for what V in, okay, we will get this point C? Anyone? Let's see who
When
can answer this.
V out equal to V in minus VTHD.
Exactly, you know that, right? So we have to find that V in for which, okay, this transistor will just enter into the saturation region, right? You know the condition for the transistor to be in saturation. That means VDS saturation, right? Or maybe if you want, I can write it now. Fourth point is to find the point C, right? So point C, it would be this VDS driver that is going to into the saturation. So that would be equal to VGSD minus VTHD, right? Isn't it? Okay. Then after, so you know the condition, but after that, in which equation you will put it?
So the V out equal to VDD minus VTNL equation.
This equation?
Yes, sir.
Why?
So because like at the transition point, it would follow
Right,
the
right.
equation.
Because this is at the edge, right? This is at the edge. So that means it is just entering, this transistor is just entering from saturation to the to its triode region, right? So you can still use this particular equation, this V out, right, and put means this particular equation and find the required value of V in, for which this transistor would go into the saturation region.
So I had a question.
Yeah.
So why are we like telling the V cutoff of the load MOSFET VTNL, like not why? Like, is there any significance to telling it VTNL, not VTHL?
I think I couldn't follow your question. Could you please repeat?
So the equation is V out is equal to VDD minus
Oh, this
VTNL, right?
equation. Right, right. This equation.
So
Okay.
why is it VTNL and not VTHL? Like, is there any significance to it?
VTNL, not VTH.
Like VTH of load.
I think I'm thinking something else. So could you please reframe your question?
So for the driver MOSFET, we
Right.
are considering VTH driver, right?
We are considering for this driver, we are considering VTH driver, right?
For the upper one also we are considering VTH only, right?
VTHL, V threshold load.
Yes, sir.
Hmm.
So that's why I was saying, like in that equation, V out is equal to VDD minus VTNL, that is VTHL only, right?
Oh, it should be VTHL.
So I'm asking, like, is it anything different or is it the same thing?
Okay, no, you see here this VTNL is in like outside, right? And then if you want to take it V threshold. Oh, okay, okay. I guess like you were asking why it is here VTNL, not V
THL
VTH
load.
load. Means why you were asking why it is load, not that D.
So no, so I'm asking why is it VTNL, not VTHL?
Okay, this is, I think, probably if you can simplify this one, it would come, to this equation only. See, here also VTH D is there, right? But VTH, you can, if you want to take it here, so both terms are present, both threshold voltage terms are present. See,
Sir, I
Okay.
think he just want to tell that instead of N, why we are not writing H. I think they
oh,
both are same.
okay, 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 okay.
So
Yeah,
yes,
yeah.
Just
that's what I was
N mod.
asking if
Oh,
they
okay,
are the
okay,
same
okay,
thing,
okay. Sorry, sorry.
or is there any
I
significance?
actually, yeah, it took quite a long time for me to understand what you were asking. Yeah, yeah, exactly. Your friend is absolutely right. So, see, I am writing this VTH. Okay, sometimes this T, sometimes this H looks like VTN. And in your book also it is written in VTN. But I have an inherent tendency from semiconductor device point of view to write threshold voltage always in VTH. So yeah, I might be also switching between these two. So please stick to any one. Okay, either it is VTN or VTH. I think better to stick with this VTH only, because generally we write like VTH N for CMOS and then VTHP for PMOS. Okay, so yeah, sorry for the confusion. So is this part clear now? Yeah, I am asking one question. Could you please confirm that? Is this part clear to you now?
Yes, sir.
Yes, sir.
Okay, thank you. Then, okay, but I would rather encourage you to really find this point. Okay, see the expression of V in. Okay, for this point, see, Okay, and like here, the point C, and the relation between this V output and V input. Just simply write the equation, equate the equation, and find the relation, right? So we are just not doing it here just to save some time. Okay, but I think as like that's what we mentioned for the resistive load inverter, we have done everything thoroughly. But from now onwards, we will try to skip some of the part which is type of repetitive, because we have understood there and we know the how the process. So just simply put the equations and find it. Okay, so there is a simple homework for all of you. So no need to note it down, because anyway this is recorded on. Also, I will share the PDF. So the it's basically says that where is my pen? Okay, so it basically says that you have an inverter with this enhancement load, right? What we are discussing earlier, and it is given that this VDD is value is 3, right? And some value like a threshold voltage of sorry, it is VTH. Okay, again it is not VTN, so I should be careful. So it is VTHD and VTHL, that is equal to 0.4 volt, right? And because both are NMOS, right? So threshold voltage is expected to be positive. Kn dash value is common for both the transistor. W by L ratio for this driver is 16 given. For the load, it is given as 2. So their W by L ratio, they are different. So when the W by L ratio become different, their driving capability is also different, right? Because ID is proportional to W by L. So please do remember that. Huh? Now here, the question says that we need to find the V out, that is this voltage, when this V in equal to 0 volt. So when this V in, you give 0 volt, okay. And instead of giving V in to be equal to 3 volt, it asks find the output voltage when V in is equal to 2.6 volt, okay. So give 2.6 volt, what would be the output? I believe if you have understood this question, the earlier concept, so it is just a matter of just putting some equation and solve it. Okay, in some cases, if you do not need the equation, like for example, the first one, if you do not need the equation, you can directly say the V out would be equal to one threshold voltage below VDD. So it is like 3 volt minus the VTH, this, like VTH of this, right? VTHL. So that would be equal to this one, 2.6 volt, right? So the V out is, you can easily find. For the other one, that is 2.6, yeah, you need the equation. You have to put it in the equation, find it. So please check it out. This is what I got. So please do cross check with me, cross check with this whether you are also getting this value or not. If you are getting some other value, maybe in the next class, please let me know. The other question is calculate the power dissipation in the inverter when V in equal to 2.6. Suppose if you have given 2.6 volt here, right, and kept it like this, then what would be the power dissipation? Again, you see here, when this transistor is on, say not even 2.6, say even if you have given one logic 1, that is 3 volt, right? Fix it here. Then this transistor is on. This transistor is always on, right? So when this transistor is on, so that means there is again a direct path from this VDD to ground. So this will again cause the static power dissipation, right? So due to this static power dissipation, again there will be a power loss, right? And this is again another issue. So for this, then there are a couple of issues, right? So which you have to identify. And okay, so this question says that you have to find the power loss. So if you just calculate the power loss by putting 2.6, find the current, then apply with the multiply with VDD, you will get the current, you will get the power loss. So that is expected to come like this, right? Then quickly, what you need to also identify the issues with this type of design. So the first one is VOH dash is not equal to VDD, right? And probably the second would be equal to VOL dash is not equal to 0 volt, right? So that means both are different from the rail voltage. The third one would be, as we have seen, the static power dissipation static power dissipation. This is another issue. So please think and tell me if I am missing any other issue. Hello. So could you please tell me, is there any other issue? Is there any other issue?
Time constant will be different.
Time constant, yeah, maybe that is too quick to now answer, because then we have to really find what is the effective resistance of this and effective resistance of this, right? So that is bit, yeah, we have to calculate it. Okay, effective resistance. But other than that, is there any other issue other than this? Other than this? Probably no, right? So these are the major, three major issues, okay, for this type of design. Okay, then compared to the previous design, what is the plus point? Plus point is that we are able to replace the the most area consuming resistor with a transistor. Yeah, I think with this we need to stop here because it is already one.
Sir,
Yeah,
so
sure. I thought like I will be able to do the next part, but anyway, yeah.
sir, so to solve this static power dissipation issue, we need such a load such that when logic 1 is applied, there should not be any direct path from VDD to ground, right?
Exactly, Shubhayan. Exactly. You are absolutely right.
So this is
Okay, you're absolutely right. We need some load, okay, so that when we give, that means what, see, static power dissipation, yeah, you were saying the, oh, wait, something again going wrong. Again, okay, again the same thing like last class. It is not allowing me to even touch. It is writing itself. Okay, so it's I'm trying with my mouse now. So, okay, so here what it
So
says
can we
is,
leave the class if we don't have doubts?
sorry.
So can we leave the class if we don't have doubts?
Yeah, sure.
Okay, sir. Thank you.
Sure. Okay, that would be better. I think if you do not have doubt, please leave. But then please give me 1 or 2 seconds. I want to restart this application so that this issue will not come again. Just be online. Open desktop. Yes, I think I am done. Done. Yeah, is it visible at your end?
yes, sir.
Okay, right. So Shubhayan, you asked about this part, and see, this is a good question. So that means this is so there will be two things. One is called, this is called the pull up network, right? You remember, right? It is called
Yes.
pull up network, right? It is called pull up network, and this transistor is called the pull down network. Okay, PDN. So it is connected like this. From here you get this output. Here it is VDD. Here it is ground, right? And a common input would be given to both of them, right? So the idea is, when you give V in equal to so V in equal to say logic 0, right? V in equal to logic 0. So that means you are expecting this output to be high, right? So that means you are expecting that it will go and charge, right? So at that time, only the pull up network will be on, this will be off. Okay. But on the other case, if you give this V in equal to logic 1, then it is like when you given logic 1, so you are expecting this voltage to be low, right? The logic 0. So that means you want this capacitor to be discharged by this pull down network. So in that case, this will not be on, but only this pull down network would be on. So if we can do some
Okay.
arrangement by selecting proper, by choosing proper network for this pull up network and pull down network, such that for logic 1 the behavior is like this, and for logic 0 the behavior is the other way, then we would be able to solve that issue. That means our output voltage can switch from rail to rail.
The CMOS inverter can do this thing, right?
Yes, exactly. CMOS
Okay.
inverter can do this, and that is the one of the most important thing. Okay, in terms of CMOS, right? Because power dissipation become minimized.
Okay, sir. Understood.
Okay. Okay then. So then let us stop here. Okay, and we will start from here in tomorrow's class. Okay then. Thank you.
Thank you, sir.
Thank you, sir.